Chapter 7 deals with electromagnetic radiation. So we want to talk about the wave nature of light. And when we deal with that, we're talking about what's called electromagnetic radiation, which is also known as radiant energy or light. And when we look at radiant energy, it's a form of energy having both wave and particle characteristics. And we're going to function more on the wave characteristics of light in this particular section. Now, when we look at the wave characteristics of light, they move through a vacuum at the speed of light, which is 3.00 times 10 to the 8th meters per second. Now, there are two descriptions about the wave characteristic of electromagnetic radiation, which we're going to cover in this particular chapter. The first is wavelength. Our symbol for wavelength is lambda, and it's described as the distance between two adjacent peaks on a wave. And our units for wavelength are nanometers or meters. And in our particular case, when we talk about electromagnetic radiation, we're going to be dealing with it in terms of nanometers, but we need to keep in mind that the speed of light is in terms of meters per second, so we'll have to do a conversion along the way. So let's look at an electromagnetic wave and deal with wavelength. Wavelength would be the distance from crest to crest or from trough to trough on that particular wave. Now, the electromagnetic spectrum has a range of wavelengths. And what we're looking at are wavelengths in terms of meters. So over here, we have 1 times 10 to the minus 12, which is for gamma rays on the left. And our wavelength increases as we go from left to right. And all the way over on the right, we have 1 times 10 to the 4th meters for our wavelength. And that's looking at radio waves like FM and AM radio waves. Now, the visible spectrum is what our eyes can actually pick up or determine. And that's in the range, very small, within our electromagnetic radiation between 4 times 10 to the minus 7 and 7 times 10 to the minus 7 meters. Now, those numbers, they're hard to deal with, so let's look at them and relate them to lengths that we're a little bit more familiar with. The waves in the electromagnetic spectrum vary in size from very long radio waves to very short gamma rays. So if we were to look over on our left-hand side of this table here, we're looking at very long radio waves. This is actually flipped from the graphic that we saw on the last slide. So when we look at long radio waves, 1 times 10 to the 2 meters, we're looking at radio waves which are about the length of a football field. As we move along and we get down to microwaves, we're looking at wavelengths on the order of 1 times 10 to the minus 2. Now, to put that into perspective, it's about the size of an insect. If we look at infrared rays, we're looking at on the order of 1 times 10 to the minus 4, and now we're looking at the size of cells. Now, if we move along past the visible light on our electromagnetic spectrum, and we move over into ultraviolet light, now we're looking at about 10 to the minus 8, and we're looking at smaller than a virus. X-rays are around 10 to the minus 10, and they're about the size of an atom. And when we talk about the wavelength for gamma rays, they're on the order of 10 to the minus 12 meters, which is about the length of the nucleus of an atom. So this graphic gives you a little bit of a perspective between wavelengths and lengths of things that we may be a little bit more familiar with. Now, if we were to take the visible spectrum and pass it through a prism, it divides that visible spectrum into its component wavelengths. And that's our colors of the rainbow: red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv. And the reason that they scatter like that is because each of those different colors has a different wavelength. If we look at the wavelengths for red, which again is trough to trough or peak to peak, that wavelength is much longer than, let's say, our violet, which has a much shorter wavelength. And then if we were to look at this in a different graphic, we have our red, orange, yellow, green, blue, indigo, violet colors, and then we've got the wavelengths kind of transposed on top of them. And notice as we go from red all the way through to purple, our wavelengths are getting smaller and smaller. Frequency is the second characteristic of a wave that we're going to deal with. And frequency, our symbol we're going to use is, looks almost like a V. It's called a nu. And it tells us the number of waves or cycles that pass a given point per second. So over on the right-hand side here, we have the graphic for 3 wavelengths. Okay, we've got red, green, and blue. And the first thing we can look at are their wavelengths. If we look at the wavelength for our red light, it's much bigger than our wavelength for green, which is bigger than our wavelength for blue. Now when we talk about frequency, frequency is how many waves per second. If we look at our red, we've got a long wavelength, and we don't have many waves per second. If we look at our green, we've got a shorter wavelength, and we've got more waves per second. And if we look at blue, we've got an even shorter wavelength, and we've got more waves per second. So when we look at this relationship, we would say that wavelength and frequency are inversely related. So we can set up an equation that deals with the relationship between wavelength and frequency. And our equation is going to be C equals lambda times nu, where C is our speed of light, which is 3.00 times 10 to the 8th meters per second. Lambda, which is our wavelength, and we need it in terms of meters so that it'll match up with our units for our speed of light. So we need to know a conversion because most of the wavelengths we're going to deal with in our problems are going to be in terms of nanometers. So for every 1 meter, there are 1 times 10 to the 9th nanometers. And then our nu stands for our frequency, and our units for frequency are reciprocal seconds, or a reciprocal second is also equal to a hertz. So here's an example. A certain violet light has a wavelength of 413 nanometers. What is the frequency for light? So when we look at this particular problem, we're given a wavelength, we're asked for a frequency. Wavelength and frequency can be related using our speed of light equation. So we write down our equation first, C equals lambda times nu, and then we're going to plug in the variables we know. We know the speed of light is 3.00 times 10 to the 8th meters per second, and that's a constant, so it will be the same for every problem. We'll plug in 413 nanometers for our wavelength, but we're going to have to do a conversion to get that to meters. So we're going to be dividing by 1 times 10 to the 9th nanometers. And frequency is what we're trying to solve for. So when we divide by our wavelength, we get our frequency, and we get 7.26 times 10 to the 14th reciprocal seconds, or hertz. Quantized energy and photons. A quantum or a photon is a specific particle of light energy. And it can be emitted or absorbed as electromagnetic radiation. And our eyes would perceive that electromagnetic radiation as different colors. The energy of a photon can be determined by an equation, which is called Planck's equation. E stands for energy in terms of joules. H is called Planck's constant. So here's another constant we need to know, and it's 6.626 times 10 to the minus 34 joules seconds. And that new variable, which we saw in our last equation, stands for our frequency in reciprocal seconds or hertz. So we have a problem. What is the frequency, the energy of a single photon, and the energy of a mole of photons of light having a wavelength of 555 nanometers? So we kind of have to think about what we're given and how we can get to what we're looking for. We're given a wavelength, so we want to calculate frequency. We're going to use our speed of light equation, and we're going to manipulate it a little bit to solve for frequency. So our frequency will equal the speed of light divided by our wavelength. So our speed of light is 3.00 times 10 to the 8th meters per second. We'll divide it by 555 nanometers converted to meters, and that will give us a frequency of 5.41 times 10 to the 14th reciprocal seconds, or hertz. Now we want to find out the energy of a photon. So we're going to use our equation that deals with energy. We'll plug in our Planck's constant value, 6.626 times 10 to the minus 34 joules seconds. We'll multiply it by the frequency that we calculated in the equation above, so 5.41 times 10 to the 14th reciprocal seconds. Notice that seconds are going to cancel out and we're going to be left with joules, and those are our units for energy. So we're going to get 3.58 times 10 to the minus 19 joules of energy. Now we want to find out joules per mole. So we're going to take the 3.58 times 10 to the minus 19 joules per photon, and we're going to multiply it by 6.02 times 10 to the 23rd photons per mole. And that's going to give us joules per mole of photons for our value, and we get 216,000 joules per mole, which is a really big number, so we can convert that to kilojoules per mole by dividing by 1,000. And we get 216 kilojoules per mole of photons in this particular problem.